Ladies and gentlemen, welcome to the Mettler Toledo webinar on quality control using thermal analysis. In order to achieve correct product quality and performance, many manufacturers have set up a number of quality control procedures to ensure that quality and specifications are consistently met. Thermal analysis is one of the many tools used to monitor the quality of materials and manufacturing processes. Thermal analysis techniques provide fast, accurate, and reproducible results. This slide lists the topics that will be covered in the webinar. First, I want to discuss the most important effects and properties that can be investigated using thermal analysis for quality control. The techniques used shall include differential scanning calorimetry, or DSC as it is usually called, thermogravimetric analysis, or TGA, thermomechanical analysis, or TMA, dynamic mechanical analysis, or DMA, melting and dropping point instruments. I will also discuss applications for each of the techniques, illustrating how they can be used to ensure product quality. I will then briefly present some features in the STAR-E software that are especially useful for quality control. Finally, I will summarize the different thermal analysis techniques and their application fields and list a number of useful references for further information and reading. Quality control is a process that inspects your products for irregularities that could compromise their quality. For example, by checking the level of crystallinity and the magnitude of the glass transition of an injection molded part, one can measure the effects of cooling within the mold. The plastic drinking glass shown on the slide shows a large crack that is due to stresses produced in the material from incorrect cooling during molding. By checking the quality of products during and immediately after production, later damage might be avoided. On the right-hand side of the slide, DSC curves are shown for a polymer subjected to various cooling rates, resulting in different ratios of amorphous to crystalline content. Once the optimum properties have been determined, this simple check ensures consistent product quality. During the webinar, I will present more details of how to check product quality using thermal analysis techniques. A basic quality control system should routinely check required specifications and use these data to create a record of the production process. The first requirement for such a system is to have a standard operating procedure, or SOP, which describes exactly how to operate any instruments used and how to prepare samples. Regular calibration and instrument maintenance is recommended, and this history should be recorded. The standard operating procedure which is finally used should be validated to test the achievable accuracy and precision of the measured results. They can be validated by using well-characterized test materials similar to the products to be examined. Quality control measurements can be assigned as pass or fail with the provision of specified pass and fail criteria. Finally, a periodic audit must be conducted to check the quality control procedures. Thermal analysis has many potential applications and is used in a wide range of industries. This slide presents an overview of the various industries and their applications. The table summarizes the most important industries and the different applications of thermal analysis in their fields. It shows that thermal analysis in quality control is mainly used to measure the purity, glass transition, melting point, thermal stability, and compositional analysis of materials. Especially important applications are polymorphism, moisture content, and oxidation-induction time determination. But let's start at the beginning. What exactly is thermal analysis? The ICTAC definition of thermal analysis is a group of techniques in which a physical property of a substance is measured as a function of temperature, whilst the substance is subjected to a controlled temperature program. The schematic diagram on the right shows a simple temperature program with isothermal and linear segments. The lower half of the slide illustrates typical events and processes that occur when a sample is heated. For example, the melting process at which the sample changes from the solid to the liquid state, and oxidation, where a sample exposed to air or oxygen will start to oxidize and finally decompose. We use thermal analysis techniques to investigate all of these effects. This slide shows 5 techniques commonly used in the field of quality control. Differential scanning calorimetry, or DSC. This is the most widely used thermal analysis technique. The picture shows a DSC sensor with a sample colored red and reference crucible. Thermogravimetric analysis, or TGA. The picture shows the sample, colored red, which is contained in a pan that is attached to the balance mechanism. Thermomechanical analysis, or TMA. Here we see the sample, colored red, positioned between the fixed and moving quartz probes. Dynamic mechanical analysis, or DMA. The picture shows one of the several available sample clamping assemblies, in this case compression mode. Melting point and dropping point instruments. The picture shows a melting point instrument with sample capillaries inserted into the instrument. It can simultaneously measure 6 samples. The last figure shows the versatile Mettler Toledo Star-E software, which is very user-friendly and easily expandable. Important quality control features such as electronic signatures, statistics, and user management are supported by the software. Let us begin with DSC. This technique allows us to determine the energy absorbed or released by a sample as it is heated or cooled. The standard Mettler Toledo DSC instruments measure from minus 150 degrees Celsius to plus 700 degrees at heating rates of up to 300 Kelvin per minute. Samples are normally measured in small crucibles made of aluminum, alumina, or other materials, typically using sample amounts of 2 to 20 milligrams. The schematic curve on the left shows a typical DSC measurement curve of a semi-crystalline substance. Exothermic effects, heat evolved, point in the upward direction, and endothermic effects, heat absorbed, downward. The features seen on the curve are interpreted and explained in the table on the right. They are 1. The initial deflection or startup transient of the DSC due to sample and crucible heat capacity. 2. The baseline where no thermal effects occur. 3. A glass transition with enthalpy relaxation. 4. Cold crystallization. 5. Melting of the crystalline fraction. And finally, 6. Oxidative exothermic decomposition. This demonstrates the large amount of information that can be gained by DSC in one simple test with small amounts of material and easy sample preparation. DSC is used to study thermal behavior and events such as melting or chemical reactions. Most of these effects are related to enthalpy changes initiated by increasing or decreasing temperature. The table summarizes the main analytical applications of DSC in the field of quality control. These applications measure various parameters such as the glass transition, melting behavior, crystallization, or thermal history of the samples. DSC measurements also provide information about the composition, purity, and polymorphism. The first application example shows the use of DSC for the quality assurance of injection-molded plastic parts. Individual batches of injection-molded parts may differ because of variations in the production process and in compounding. DSC is one of the techniques that can show differences between the batches. The diagram in this slide shows the DSC measurement of two different batches of the same thermoplastic seal. One batch has good performance, as demonstrated by the green curve, and the other batch fails during use, which is shown in red. If the seals are heated above their glass transition temperatures of 145 to 155 degrees Celsius, the unstable material from the red curve will reorganize and crystallize. Upon crystallization, seen at 170 degrees Celsius in the red curve, the bad material shrinks and its mechanical properties change. The material then fails during use. DSC measurements thus present a quick and easy detection method for badly produced batches and help in setting the quality parameters. With the current slide, we will discuss the solid fat index of edible oils. The solid fat index is a measure of how much fat remains in the solid or crystalline phase at the temperature of interest. For foodstuffs, this is an important quality control parameter, since solid fats have completely different mechanical properties when compared with liquid fats, and this affects the texture felt in the mouth. For example, chocolate needs to be firm at room temperature, and it should only melt at higher temperatures, specifically the temperature at which it is eaten. Mayonnaise, in contrast, needs to be spreadable at room temperature and below. Therefore, chocolate needs to have a much higher solid fat index at room temperature than mayonnaise. The solid fat index of a wide variety of foodstuffs and ingredients can be quickly and easily ascertained from DSC measurements. The example here shows the measurement of the solid fat index of palm oil. Palm oil is semi-solid at room temperature, and it consists of two phases. One phase is the palm stearin, which contains the higher melting fats. The other phase is palm olein, which contains the lower melting fraction. The DSC curves of native palm oil and its two fractions thus exhibit different melting behavior, as can be seen in the upper left corner of the slide. The native palm oil is shown in red. The lower and higher melting fractions are both present. The pure olein is shown in blue, and we can see that it contains mainly the lower melting fraction. The stearin is shown in black, and when compared to the native palm oil, we see that the higher melting fraction is present in higher concentrations. If we plot the conversion factors from the DSC melting peaks, as shown in the lower left corner of the slide, we can see that the liquid fractions for each phase increase with temperature, but not equally. By taking 100% minus the liquid fraction, we now obtain the solid fat index and can easily read off how much solid is present at a particular temperature. This can now be used as a criterion to choose ingredients for specific foods. Now let us turn our attention to thermogravimetric analysis, or TGA. In this technique, the mass of a sample is continuously measured as it is heated or cooled in a defined atmosphere. We simply put a few milligrams of the sample into a crucible, weigh the sample, heat it, and record the weight change. From this, we can obtain information about the composition of the sample, such as the polymer and filler content. The schematic curve on the left shows a typical TGA measurement curve of a polymeric composite material. Initially, before the heating ramp begins, the TGA measures the mass of the sample. At the end of the measurement, inorganic fillers, such as glass fibers, remain as a residue after heating to temperatures of 1000 degrees Celsius. The loss of mass at each step relates to the behavior of the material's components. The steps are numbered next to the curve and explained in the table, namely, 1. Heating begins and volatile components vaporize. 2. Pyrolysis of organic substances and polymers. 3. At 600 degrees Celsius, the atmosphere is switched from nitrogen to air to obtain oxidative conditions. 4. Carbon black or carbon fibers burn. 5. Inorganics such as glass fibers or talc filler are left behind as a residue. For different types of materials, different decomposition curves will be measured. Modern TGA instruments often provide simultaneously measured DSC or DTA curves together with the weight loss information. This confirms the nature of the weight loss, for example, energy released by decomposition. The table summarizes the main analytical TGA applications used in the field of quality control. TGA provides information about the sample composition. It allows us to check the thermal or oxidative stability of products and provides information about the content of moisture or volatiles in formulated products. Where TGA is used to investigate processes such as vaporization or decomposition, evolved gases can be analyzed using hyphenated techniques such as TGA-MS, TGA-FTIR, and TGA-GC-MS. The picture on the right is a view of the open furnace showing a sample holder with two positions for the sample and reference crucibles in a simultaneous TGA instrument as mentioned in the previous slide. The standard crucibles are made of aluminum oxide, alumina, in order to withstand high temperatures. Cement consists of many different minerals, one of which is gypsum. Gypsum is a very important additive as it slows the hardening of cement in the range of 10 minutes to several hours or even days. The added gypsum is a mixture of hemihydrate and dihydrate forms. It is important to know the relative quantities of both to control the quality of cement. Since dihydrate and hemihydrate lose their water of crystallization at different temperatures upon heating, thermogravimetric analysis is an ideal method to determine the amount of each component. The slide shows a pure dihydrate sample in the blue curve, which loses its first water of hydration from 100 degrees Celsius upwards, and its second water of hydration from 150 degrees Celsius onwards. Dehydration of the dihydrate is expected to show a total mass loss of 20.9%. 15.7% is due to the dihydrate mass loss between 100 and 150 degrees Celsius, and then 5.2% is lost from the hemihydrate above 150 degrees Celsius, this being equivalent to a mass loss of 1/2 water of crystallization. The pure hemihydrate, shown in black, only has 1/2 water of crystallization, the loss of which matches the second mass loss step of the dihydrate seen above 150 degrees Celsius. By comparing the temperatures and the ratios of the mass losses of pure hemi and dihydrate samples, these quantities can now be determined in unknown gypsum samples. A measured curve of an unknown gypsum sample is shown in red. It is clear from the curve that this sample is a combination of hemi and dihydrate. Pencil lead hardness is a very important property in pencil production and therefore an important parameter to check during quality control. Pencil leads generally consist of a thermoplastic matrix into which fillers are incorporated to regulate the hardness of the resulting leads. Traditionally, the polymer matrix consists of cellulose, which is slowly being replaced by other thermoplastic polymers. The main fillers are clay and graphite. The amount of clay defines the hardness of the pencil lead, the amount of graphite the darkness of the marking. Since the hardness of the pencil leads is due to the amount of clay, the hardness can easily be tested by measuring the inorganic clay residue with thermogravimetric analysis. Different hardness pencil leads were measured in an inert atmosphere up to 600 degrees Celsius, and at this temperature the gas was switched from nitrogen to oxygen and heating was continued to 900 degrees Celsius. The hardness grading system shown is the European system, where the letter H stands for hard and B for black. The hardest grade measured here was 6H, and the softest grade was 5B. As shown in the figure, different grades of lead lose different amounts of their mass in the temperature range from about 100 to 400 degrees Celsius. This first mass loss step is caused by the vaporization of additives such as oils and waxes. The amounts of these components are clearly not related to the degree of pencil lead hardness. The second mass loss, after the switch to oxygen, is due to burning of the residual polymer matrix and graphite. After the burning step, any residue that remains behind is inorganic matter, namely the clay filler. There is a clear correlation between the remaining inorganic residue at the end of the measurement, which is the amount of clay, which defines the pencil lead hardness. This means that the amount of residue from the TGA measurement can be used as a quality control testing parameter for the pencil lead hardness. I now want to move on to thermomechanical analysis, or TMA. This technique measures the dimensional changes of a sample as it is heated or cooled. The schematic curve on the left shows a typical TMA curve of a sample measured in the compression mode using a small applied load. The different effects are numbered next to the curve and explained in the table, namely 1. Expansion below the glass transition. 2. The glass transition point at which the rate of expansion changes, as observed by the change in slope. 3. Expansion above the glass transition. The steeper slope indicates a greater rate of expansion. 4. Softening with plastic deformation or viscous flow. The table summarizes the analytical applications of TMA in the field of quality control. One of the applications is the determination of the expansion behavior and the coefficient of thermal expansion, or CTE. TMA is also an excellent technique for determining glass transition temperatures, for studying softening behavior, polymorphism, and swelling behavior in different solvents. The picture on the right shows a typical experimental setup of a ballpoint probe in contact with a sample. An important quality control parameter for gaskets or other elastomeric products is their deformation under the influence of an applied stress and their return to their original shape upon the removal of that stress. If the material flows under stress, it might not be a suitable seal between joints, and leakage could occur. The flow behavior can easily be measured with TMA or thermomechanical analysis. This slide presents creep measurements of 4 styrene butadiene rubber samples, abbreviated as SBR, each having a different degree of vulcanization. The sample designated as SBR1 does not contain any cross-linking agents, while SBR2, SBR3, and SBR4 contain increasing amounts of cross-linking agent, in this case sulfur. For the determination of the initial baseline, a small force of 0.01 Newton is used, which causes no significant sample deformation. For the deformation segment, the force is increased to 1 Newton. The samples undergo creep, which lessens with increasing vulcanization due to the restraint imposed by the crosslinks. The material deformation is desirable when the elastomers are used for sealing purposes, but when the stress is removed from the material, they should ideally return to their initial form. This is assessed in the experiment by lowering the applied force from 1 Newton to 0.01 Newton. As soon as the force is lowered, all 4 SBR materials show creep recovery back towards their original shape. As the degree of cross-linking decreases from SBR4 to SBR1, the irrecoverable deformation, known as irreversible viscous flow, increases. TMA thus provides a quick and simple test for the behavior and quality of elastomeric seals. The second TMA example shows the delamination and decomposition of a printed circuit board. Printed circuit boards are made of woven fiberglass embedded in an epoxy resin matrix and are used for mounting electronic components. Since the printed circuit boards are often used in confined spaces with hot components, they can heat up considerably during operation and might be at risk of degradation. The thermal stability of the boards is therefore an important quality criterion. For the measurement shown on the slide, a disc of around 4 millimeters diameter and 1.6 millimeters in thickness was analyzed using a ballpoint probe with a load of 0.05 Newton. The sample was first heated up to 100 degrees Celsius to remove any memory effects, then cooled and heated from 30 degrees Celsius to 500 degrees Celsius at 20 degrees per minute under a protective atmosphere of nitrogen. The PCB sample exhibits a change of the coefficient of thermal expansion at 92 degrees Celsius, which can be interpreted as the glass transition of the matrix material. The appearance of noise on the curve at about 320 degrees Celsius indicates that the sample begins to delaminate at this temperature, with the complete decomposition of the PCB starting at around 360 degrees Celsius. To find out which gases are released during the decomposition, the capillary of a mass spectrometer was introduced into the furnace of the TMA and kept there during the measurement. From the recorded masses, only the traces for M/Z 70 and 94 are shown. These masses indicate the presence of bromine and of methyl bromide. Both products are typical decomposition products of tetrabromobisphenol A, or TBBA, a flame retardant. Reaction products containing bromine can even be detected immediately after the glass transition. The rapid increase in the formation of bromine-containing decomposition products above 330 degrees Celsius also indicates the reason for the delamination process. Dynamic mechanical analysis is used to measure the mechanical properties of a viscoelastic material as a function of time, temperature, and frequency when the material is deformed under a periodic oscillating stress. The schematic diagram on the left shows the results of a DMA heating measurement of a crash-cooled semi-crystalline polymer in shear mode. The curves display the storage modulus G', the loss modulus G', and tan delta as a function of temperature. The different effects are numbered next to the curve and explained in the table on the right, namely 1. Secondary relaxation, observed as a peak in G', and tan delta. 2. The glass transition, seen as a decrease in the storage modulus and as a peak in G', and tan delta. 3. Cold crystallization begins with increasing temperature. 4. Recrystallization accompanied by a peak in G', and tan delta. 5. Melting of the crystalline fraction with a decrease in the storage modulus and a large increase in tan delta. The table lists the main DMA applications used in the field of quality control. DMA can provide information about the modulus, damping, and viscoelastic behavior of materials. Also, the glass transition temperature, softening temperature, and sub-TG processes, such as the beta relaxation, can be measured. The picture on the right shows a sample installed in the DMA ready for measurement in bending mode. When materials go through the glass transition, they soften from an amorphous solid with a high modulus value to a much weaker rubbery or liquid material. This means that the glass transition temperature at which this softening occurs is a very important quality parameter for products whose mechanical integrity is important. The example on the slide shows the decrease in stiffness of a composite consisting of a matrix material reinforced with glass fibers. Such materials are used, for example, in the airplane and transport industries. Because of the glass fiber reinforcement, the material shows a relatively small modulus change at the glass transition, which is nonetheless easily detected, even for such a highly filled material as that shown here. Other techniques, such as DSC, might fail due to the overwhelming mass of the fiber content. The example shown here was measured using single cantilever mode at a frequency of 1 Hz and with a heating rate of 5 Kelvin per minute. From top to bottom, the diagram shows the curves of the storage modulus, G', black axis, loss modulus G double prime, red axis, and tan delta, blue axis. Two effects are observed. Below 100 degrees, a beta or secondary relaxation is visible in the tan delta and loss modulus curves. This secondary relaxation process is caused by the onset of local mobility in the measured materials. The most prominent effect is the glass transition at about 190 degrees Celsius, and the temperature can be used as a measure of the state of cure, higher temperatures indicating a greater degree of cure. For engineering applications, for example aircraft wing components, the composite material cannot be used at temperatures above the indicated onset, after which the modulus drops rapidly. With the Mettler Toledo melting and dropping point systems, the temperatures for the melting point, the melting range, the dropping point, and the softening point of materials can be determined automatically. In comparison with the other techniques discussed, this method is very simple and can be used by less skilled operators. The melting point instrument determines the temperature at which materials change from the solid to the liquid state, that is, their melting point. If the transition is not sudden, but happens over a certain temperature region, the effect is also called the melting range. The measurement can be performed with up to 6 capillaries at the same time, allowing either duplicates or several materials to be measured in one experiment. Both the melting point and melting range evaluations are performed according to the pharmacopoeia guidelines. Since the melting point of a pure substance is highly dependent on its purity, the measurement can also be used to evaluate the purity of chemical substances. The dropping point instrument records either the temperature at which the first drop of a substance falls from a cup under defined test conditions, or the temperature at which highly viscous samples, which do not form droplets, have flowed out of the cup over a certain length. Both of these parameters can be automatically determined on 2 specimens simultaneously. Measurements of the dropping point of lipstick are shown on the current slide. Lipstick contains a mixture of pigments, oils, waxes, and emollients. Dropping point experiments are commonly used during quality control measurements as they can help identify and characterize different waxes such as paraffin, natural waxes, or microcrystalline polyethylene. The table at the top of the slide shows results of duplicate measurements of 3 different lipstick samples, which were measured according to the ASTM D3954-94 standard. The repeatability of the duplicate measurements was very good. The lower right corner of the slide shows 2 screenshots taken during the analyses. Several options in the Mettler Toledo STAR-E software provide easy-to-use quality control possibilities. One of these is the reference curve feature, which is illustrated on the current slide. This feature allows the user to select a previously measured curve of a known good quality product from the database and use this as a reference curve against which to compare new product batches. The user can choose the upper and lower tolerances for achieving good quality product. The measured curve from the new batch is then displayed between these limits during the test. With the help of this software feature, the quality tester can immediately see if the tested product is within the specified tolerances. Often, quality control laboratories routinely perform the same measurements again and again. Any step in the quality control process that can be automated will therefore be able to save time and money. One feature which is included in the Mettler Toledo software allows users to do just that. Users can edit curves, set limits, choose types of evaluations, and validate the generated results automatically. Such analysis routines can even be connected to a method, so that results are produced immediately on completion of the experiment. An example of such an automatic evaluation is shown on the slide. The melting of high-density polyethylene was evaluated automatically, and the result was tested against upper and lower limits. The slide shows the predefined message, displayed in red, that the sample has passed. Another feature of the quality control software option is that quality checks of different batches, production lots, types of materials, etc. can be statistically evaluated and trend lines can be plotted. This slide shows the DSC melting curves of polypropylene polyethylene copolymers. Copolymers are frequently used as they are more economical and their properties can be tailored to specific applications. Therefore, it is very important to check the copolymer composition to ensure that products can meet the correct specification. To verify this, the melting of the copolymer batches was measured to check the relative amounts of polypropylene and polyethylene. The statistical analysis of the results can be plotted in the same figure. The results obtained can also be exported to external software where more advanced statistical evaluations can be performed. One such example is shown in the lower left corner, where a control chart is plotted. Any unexpected deviations can immediately be detected and corrective actions can be taken. The table summarizes the most important properties that can be used to check the quality of products under investigation. The table makes recommendations for the preferred techniques for investigating each effect. A box marked red means that the technique is strongly recommended. A box marked blue indicates that this technique can also be used. The most important effects that can be analyzed by DSC are the melting behavior, glass transition, chemical reactions, and the influence of fillers. The main applications of TGA are content analysis, thermal stability, and evaporation behavior. TMA is normally used to study the expansion, shrinkage, or melting behavior of materials, and uniquely CTE. DMA is the best method for characterizing the viscoelastic behavior of materials, including glass transition measurement, especially for composite materials. DP is used to detect dropping and softening points and is useful in routine testing. MP is used for automatic melting point and melting range detection, and again is useful in routine testing. This slide gives an overview of the temperature ranges of the Mettler Toledo DSC, TGA, TMA, DMA, and thermal values instruments. In general, DSC experiments are performed at temperatures between minus 150 degrees Celsius and plus 700 degrees. The temperature ranges may be different if special equipment or accessories are used. TGA measurements normally begin at room temperature. The maximum possible temperature is about 1600 degrees. TMA experiments can be performed between minus 150 degrees Celsius and plus 1600 degrees. DMA samples are measured in the range minus 150 degrees to plus 500 degrees. Thermal values include melting and dropping point instruments. Their temperature ranges depend on the version of the instrument and are shown on the slide. Finally, I would like to draw your attention to information about the use of thermal analysis in the field of quality control that you can download from the Internet. Mettler Toledo publishes articles on thermal analysis and applications from different fields twice a year in UserCom, the well-known Mettler Toledo biannual technical customer magazine. Back issues can be downloaded as PDFs from www.mt.com/TA-usercoms as shown in green on the slide. In addition, you can download details about webinars, application handbooks, or information of a more general nature from the Internet address given on this slide. This concludes my presentation on quality control with thermal analysis. Thank you very much for your interest and attention.